Let h be a continuous function. Let h be a continuous function on the unit disk not unit disk, unit circle. Then there exists a harmonic function. There exists a harmonic function denoted by h tilde on the unit disk T, which extends continuously to the boundary of this unit disk, which is a unit circle, which is a unit circle, and h tilde z approaches to h of zeta as z from the unit disk tends to any point on the unit circle. So this is the problem, and how we have to construct this function h, and the construction of this function involves a theory, and that I will discuss later on. That's theory of Poisson integral and a Poisson kernel. But before that, I'm going to introduce to you a function for z to be a point in the unit disk. We define this number pr theta to be defined by this infinite series r power mod k eik theta, and this this function, which is a function of r and theta, this is called Poisson kernel. This is called Poisson kernel. So let us see whether this is a well-defined thing or not. Let us fix some number rho less than 1. Then you see for any positive r which is smaller than this rho, we have modulus of r power mod k e to power I k theta, its modulus. This is equal to r power mod k, and this is nothing but this is less than or equal to, since r is less than or equal to rho, it is rho to power k. And you see that this geometric series, since rho is a less than 1, so this geometric series r power mod k, rho power mod k, I don't have anything modulus with this. So this is convergent, and once it is a convergent, you see that by Weierstrass M-test, we get to see that this series is a convergent to uniformly convergent. By Weierstrass M-test, we see that this series, which defines this Poisson kernel e to power I k theta, is uniformly convergent on mod z less than or equal to rho. So it is uniformly convergent on, you can say that, on compact. So it will follow that it is uniformly convergent on compact sets of unit disk as well. So this is a well-defined property. There are some immediate properties of this Poisson kernel. For example, we have this series PR theta k equals to minus infinity to infinity r to power mod k e to power I k theta. If I break this into two parts, k from minus infinity to minus 1, And by the definition of then mod, it has to be r power minus k ei k theta plus k from 1 to infinity, it has to be r power k ei k theta. In the first summation, if I make a change of variable, what change of variable? I'm going to replace k by minus k in this first summation, then I will get this range of summation from 1 to infinity, and I will have r power k e to power minus I k theta plus I will have k from, it is the second summation is running from 0 to infinity, r power k e to power I k theta. And now you see I can write, if we take z to be rei theta, what this comes out to be in first summation, this is equal to z conjugate to power k, it is z conjugate to power k, and k running from 1 to infinity, and I'm going to put k equal to 0 in this second summation, so I can write 1 separately, and then I will have another series k from 1 to infinity, it is z to power k. And clearly you have z in the unit disk, its modulus is less than 1, and so we know what are the sum of these two geometric series. And so the first sum will be 1 upon 1 minus z conjugate 1 plus another sum will be 1 minus z. So we have this formulation of a Poisson kernel also. Theta for z equals to rei theta, we have this thing also. Now let us further simplify it, taking out the LCM. If you take out the LCM, taking LCM, what we are going to get, another immediate thing that I can get is 1 minus z into 1 plus z conjugate plus z into 1 minus, so what is it z? No, let me see. Whether I have written this power series accurately or not. Yeah, the sum of this geometric series has to be z conjugate, this has to be z. Okay, that's it. So then I have to simplify it again. So now you take out the LCM, what you will get this thing, 1 minus z conjugate into 1 minus z, then I will have z conjugate into 1 minus z plus z into 1 minus z conjugate, and I will have 1 minus z conjugate into 1 minus z, and you know 1 minus z conjugate is equivalent to write 1 minus z whole conjugate, and you know z into z conjugate is mod of z square, so it will be 1 minus mod z square, and plus if you simplify these terms, you will have z mod minus mod z square plus z minus z into z conjugate will be mod z square. In numerator you will have denominator also you will have 1 minus mod 1 minus z mod square. So you further see this 1 minus mod z square has to be something that you can further simplify into something. what it is going to be. This you have z equals to r e I theta, and better to write this. But better to multiply these numbers 1 minus z into 1 minus z conjugate. So it will be 1 minus r e I theta into 1 minus r e minus I theta. Let us multiply these numbers and see what we have. 1 minus r e minus I theta minus r e I theta plus I will have r square, and the rest will be cancelled out. You write 1 plus r square, and you may write it as minus r and e I theta plus e to power minus I theta, and you divide it by 2, and you multiply by it by 2, and then you see something that is in bracket is a cos theta. So it will be 1 plus r square minus 2r cos theta. So we have this number. So let us see what substituting this in here, what we get. And also at the same time, I have z conjugate and z. I have some of these two numbers, and you know that's number plus its conjugate is twice of real part of that number. And real part of that number means 2r cos theta it has to be. And mod z square, you have 2 times this minus mod z square and minus mod z square, and z is r e I theta, so mod z square is r square theta. So we have this numerator equals to 1 plus r square theta minus twice r cos theta plus 2r cos theta. Z plus z conjugate is 2r cos theta minus 2r square, and in numerator we have 1 minus mod z whole square, that is equal to 1 plus, again as I calculated in the numerator, my 1 plus r square minus 2r cos theta. And see what is left to you. What is left to you is 1 minus r square upon 1 plus r square minus 2r cos theta. So this is another expression for this Poisson kernel. So there are other properties also that I will leave for you as a assignment, 3 or 4 properties which I'm going to just state for you, and some of the properties that you have to verify for this Poisson kernel are the following. The first thing, that it is a probability measure over the interval minus pi to pi. The probability measure means its integral is 1. You have to prove this thing. And the second is that it is a even function of theta, and theta is over restricted to this interval. There are some properties which directly follow from the definition, so it is always positive on this interval in case of theta, whatever r it is. As a function of theta, for fixed r it is increasing. This is increasing on minus pi to 0, and this is decreasing on 0 less than equal to theta less than equal to pi. And you see you have this, if you fix some r, and you see as what kind of behavior this p and kernel. Once I say that it is even function pr minus theta is equal to theta, that means it is symmetric with respect to y-axis. And then if so it seems that it is symmetric with respect to y-axis. And then let me write other properties also, then I will see what it happens. And if I fix some positive delta, then maximum of this function PR theta over this interval delta less than equal to theta less than equal to pi, this maximum value tends to 0 as r tends to 1. So as r tends to 1, the maximum of this graph will tend to 0. But what these two properties say is it is positive, it lies above x-axis. It is a even function of theta for fixed value of r, so it is symmetric along the y-axis. So you can guess that it might look like a bell-shaped curve. Yeah, it has to be peak somewhere here. It might look like this thing because it is symmetric along. It has to be reflecting image along the y-axis. It has to be positive. It has to be first increasing, and then from 0 onward, it has to decrease. So it definitely has to be bell-shaped kind of thing. And the last thing that is very clear is that this PR theta is a harmonic function of Z, harmonic function of Z. And showing that this is a harmonic is not a big deal because we just show that PR theta is something 1 plus Z upon 1 minus Z conjugate plus Z upon 1 minus Z. And if you first simplify this, you will get that this thing is nothing but this real part of this function 1 plus Z upon 1 minus Z. So once you see that it is a real part of some function, and what function it is, this is function, you know that this function is analytic. This function is analytic on the unit disk. And once you know that it is a real part of an analytic function, what we know about analytic functions that their real and imaginary part both are harmonic function, and hence it follows that this PR theta is a harmonic function. It is harmonic function. So other properties that you have to put as an assignment and you have to prove all those properties. So noting down these properties, let us move to the proof of the theorem that a continuous function on the unit circle can be extended to be harmonic function, uniquely harmonic. It can be extended uniquely to be a harmonic function inside a unit disk. So let us define something. I'm just starting now the proof of the theorem. Let me define a function h tilde of z to be integral minus pi to pi. H is a given function, h on the unit circle, hei theta, and pr theta minus phi d. It is not theta, hei phi I am taking. It is d phi upon 2 pi for z equals to r ei theta. This is the function. So one thing is clear that h is continuous, PR being harmonic is continuous. So this integral is well defined and the integral of this function exists. So this is a complex valued function and it is a well defined function. This is clear. And let us, if we write h in its real and imaginary parts, if we decompose h in its real and imaginary parts, I can write h as u plus iv. Then we, since PR is a real, we don't have, this is not complex valued. This Poisson kernel is real valued always. So depending upon the decomposition of h, we get the corresponding decomposition of this h tilde, and let the real part of this h tilde be denoted by u tilde z. It will be minus pi to pi, and real part of this h u e I phi pr theta minus phi d phi upon 2 pi, and we will have v tilde z to be minus pi to pi u, it has to be v e I phi P r theta minus phi d phi upon 2 pi. Now let us see first this u tilde. What is this u? This you have u tilde z is equal to minus pi to pi, and it is u e I theta p r theta, it is e phi minus phi d phi over 2 pi. Now what is u? U is a real part of h, and pr, as I said in the last property, pr theta minus phi has to be it has to be real part of ei phi minus plus z upon ei phi minus z. It is a real part of this function. So if you see these things, then we get this u tilde to be real part of some function. This u tilde is nothing but this is a real part of integral minus pi to pi. It is h r we can take this to be real part. Or we might keep it as a real part of u, but it is better to take real part of h. It is real part of, no, it has to be u. It has to be u, because in multiplication we cannot write. It has to be real part of. It has to be real part u, and we don't require to write it as real part of h. Otherwise, real part of h into real part of this, we cannot write this real part of zw to be a real part of z dot real part of w. So I have to consider it as only real part of this function u e phi as it is into ei phi plus z upon ei phi minus z into d phi upon 2 pi. Now, what is this real part of? What is this integral? If you look at this integral, in previous semester we have seen that such type of integrals are always analytic functions of z. This is analytic function of z. What we call it as it varies analytically with z. It is analytic function of z. It varies with z as analytically, and so it is an analytic function of z. It might be a good exercise for you to verify that this is an analytic function. And whenever you take a continuous function and you define in this way, you are going to always get this as an analytic function. So this is an analytic function, and now you see that this u tilde is a real part of some analytic function, and you know that the real part of an analytic function is always a harmonic function. So it follows that now that this u tilde is a harmonic function. This is a harmonic function. So this has been established that u tilde is a harmonic function, and likewise the imaginary part of h tilde, that is the v, will prove to be a harmonic function. Likewise v tilde is a harmonic function. So u and h tilde both are harmonic function, hence h tilde, which is made up of these two functions, u tilde and v tilde, is harmonic. It is a harmonic function because it is a complex valued harmonic function, and a complex valued harmonic function is harmonic when its both real and imaginary part are harmonic. So one thing that we proved about this h tilde is a harmonic function, and to complete the proof, the only thing that remains to prove is that this h tilde at z tends to h of zeta for z in d when tends to zeta in the unit disk. we have to show that on the boundary it is equivalent to say that on the boundary these two functions agree. That is, you can say that on the boundary these two functions agree. So let's do this thing now. And you know this unit circle is a compact set, and on compact sets every continuous function is a uniformly continuous function. So H is a uniformly continuous function, and on compact sets continuous functions are bounded also, and H is bounded as well as uniformly continuous function. So I must write that since this boundary is compact, this is a compact set, so H is uniformly continuous, and bounded on the and bounded on this unit circle. So uniformly it is bounded means, so let us set the bound. So let M be the bound be such that mod of H E I theta is less than or equal to M, and let epsilon be a positive number, now using the uniform continuity. So there exists some delta number greater than 0 such that I will have this H E I theta minus H E phi to be less than epsilon whenever you will have theta minus phi to be less than delta. This is a uniform continuity of this function. Now we have to show that H tilde Z converges to H on the unit circle. Let us try to look at this estimate, this number. So H tilde is given by the integral representation minus pi to pi. It is H of Z is R E I theta. Or what I'm going to do, I'm going to just write this, replacing this. I'm just writing it as E I theta minus phi minus H of E I phi. This is E I theta. No, not. Let me take one more step to write this thing. Let me change the color as well. So this is minus pi to pi H E I theta minus phi into P R phi d phi upon d 2 pi. We had this E I theta, but I'm replacing in this notation where I have defined H. I have defined H P R theta minus phi. So replacing theta minus phi by phi. So ultimately E I phi has to be replaced by theta minus phi. So this is what I'm doing here. Minus we have H E I theta also, but I can write H E I theta into integral minus pi to pi. This is the property of this Poisson integral, that is a probability measure. So this total integral is 1. And so I can write this now, integral being a linear function. I can separately like H E I theta minus phi minus it is H E I theta into P R phi d phi upon 2 pi. So now I'm going to break down this integral into two parts, because on a certain part minus delta to delta we have some estimate for this difference of H E I theta minus phi and this number. So I'm going to break it into two parts, and the one part is minus delta to delta of integral, and the other another part I'm going to remaining is what delta greater than phi less than or equal to pi, less than or equal to pi. We have this thing, and whatever integrand we have, I'm not going to repeat it. So let's take the modulus of these terms now. H E I H Z, it is H Z minus H E I theta, and it will be less than or equal to, once you take this modulus inside the integral, it would be less than or equal to minus delta to delta. It has to be H E I, it is theta minus phi minus H E I theta, and you know that this Poisson integral is a positive function, so let's keep it out of this modulus. Plus we have delta less than or equal to phi less than or equal to pi, and I have to write it as H E I theta minus phi minus H of E I phi, E I theta P R phi d phi upon 2 pi. In the first integral, I can use this uniform continuity, and this will give me to be less than, it will be less than epsilon, and I have this integral minus delta to delta, and I can write this, replace this integral to be minus pi to pi, because that is a larger domain, and our larger domain integral of a positive number becomes larger, so it is PR phi d phi upon 2 pi. And similarly, now I'm not going to use in the second integral here. Let's first use the triangular inequality, and then use the boundedness. And so then I will have this h is less than or equal to m, and another h is also less than or equal to m. So I will have twice of m. And again, I'm going to increase the domain of integration from delta up to pi to minus, this is 2m actually, minus m to or not let's keep this only it only delta less than or equal to phi less than or equal to pi, and this is mod p r phi d phi upon 2 pi. And you see now the first integral is going to be 1, and in second we are not going to use this one, we are going to use something different. So this is going to be less than or equal to epsilon plus I'm going to now take this to be, it is 2m, and I'm going to take it to be maximum of delta less than phi less than or equal to pi, and p r phi. This is what I'm going to take the maximum of this function p r theta over this part delta to pi, and rest we will be having d theta upon 2 pi, d phi upon 2 pi, and the integral of that value that is going to be 1. And we have this estimate now. Now the property that we just stated here of this is also a property that this maximum of this Poisson integral tends to 0 as r tends to 1. So what we can see now, that this number hz minus h, this is h tilde z, h e I theta, this tends to we have only epsilon as r tends to 1. What we can see now, we can say that this value h tilde z clusters to within epsilon of h e I theta as z tends to the boundary. Now what it means, that, but since you have epsilon to be arbitrary, was arbitrary, is arbitrary, so it must be true that this tilde h tilde z tends to h e I theta as z which is r ei theta, you must, it may be eri anything, it tends to ei theta. You have this established. Now this is true for every ei theta, every z. So this completes our proof that h tilde is the required function, which is the extension of this h to the interior of a circle, that is the unit disk, and it accumulates, or it becomes an extension of this h inside the, and why it is, why this extension is a unique, let me write it, its uniqueness also. Uniqueness says that suppose you have two functions, suppose h tilde and some k tilde are two such functions, two such extensions, then extensions of h, then what you have, they are different extensions, then since these extensions agree on the boundary, they agree on the boundary, that is mm, that is on the boundary, h tilde minus k tilde is equal to 0, because they converge to the same thing, they are the extension of the same function on the boundary. So on the boundary they send, so by maximum principle, because on boundary they are 0, so inside the boundary their maximum is also going to, by maximum principle, they are harmonic functions, no? By maximum principle, h tilde minus k tilde is equal to 0 in unit disk also. That is to say that h tilde is same as k tilde on the unit disk, hence the uniqueness. Hence the uniqueness. So this is important, that they are unique. And what we actually did here in this proof, we had h, from h we defined a function h tilde, and h tilde was defined to be a function as integral from minus pi to pi as h of ei theta pr theta t. Phi, let me take it to phi theta minus phi. Okay. This pr theta minus phi, it is d phi upon 2 pi. So corresponding to every continuous function on the unit disk, it is a unit disk function, we have been able to construct a function on the unit circle. The unit on the unit circle, we have a h defined on unit circle. We've been able to construct a harmonic function on the unit disk. So we have this correspondence of h to h tilde, and this function is given a name. This is called a Poisson integral. This is called a Poisson integral of h. This is called a Poisson integral of h. So we have this mapping h to its Poisson integral. Every continuous function on the unit circle can be extended through Poisson integral to a harmonic function in the unit disk, and this correspondence is linear. One of the thing is linear, that if you have two functions h1 plus h2, and if you find their Poisson integral is going to be Poisson integral of h1 plus Poisson integral of h2. Not only addition, if you multiply it with any scalar alpha and any scalar beta, you are going to this alpha plus beta. So this Poisson integral is a linear. Why it is a linear? It is very quite obvious that this is integral of some function, and integral is a linear function. Another thing that you might observe, that the maximum principle holds in the sense that if h of ei theta is bounded by some number, obviously it is bounded on by number, then you see that what is the modulus of h tilde? It's Poisson integral now, better to call Poisson integral, and it has to be less than or equal to minus pi to pi, it will be mod of HEI phi. It is PR theta minus phi d phi upon 2 pi. And since the integral of this modulus of this h is less than or equal to m, and this is less than or equal to m, and what is left to you is the integral of the Poisson kernel, and the Poisson kernel integral is 1, and this integral is 1. So you this is bounded by same m. So this is bounded by same m. This is what I used in proving this uniqueness theorem. So this is all about that we had about Poisson integral.